This is the chemistry of water, and we'll cover chapter 14 of your textbook. Just starting out with some very basics of water before we transition into more applications of why water is so important. One of the key aspects of water is that it is an oxygen atom that is connected to two hydrogen atoms. The way that water is organized makes water polar. And if you remember, polarity is when the electrons hang out around one atom in a molecule much more so than other atoms in the molecule. In water's case, the electrons hang out around oxygen because oxygen is much more electronegative than hydrogen is. This creates the oxygen end of the water molecule to be negatively charged. That then makes the hydrogen ends of the water molecule positively charged. So the molecule itself has an area that is negatively charged and an area that is positively charged, and we call this polarity. It's important to know, though, that water is not charged because the number of electrons and the number of protons within a water molecule are equal. Water itself carries no charge. The polarity of water allows it to create these special types of attractions that are called hydrogen bonds. And we've talked about hydrogen bonds before. Remember that hydrogen bonds are formed when you have an electronegative atom, like oxygen, nitrogen, or fluorine, that's attracted to the positively charged hydrogen. A hydrogen bond itself is relatively weak, but if we were to have like a glass of water, there are tons of hydrogen bonds. So it in itself is strong. Hydrogen bonds are actually the strongest type of intermolecular attraction that exists. Because of the properties of water that we just discussed, its polarity and ability to make hydrogen bonds, there are some very important properties of water that we're going to discuss. Those are cohesion, adhesion, high specific heat, and high vaporization. Oh, and then there's one more, the fact that water is less dense as a solid than it is as a liquid. So starting with cohesion, the definition of cohesion is the ability of something to stick to itself. So specifically, the attraction between particles of the same substance. So this is when we're talking about cohesion, we're talking about the hydrogen bonds that water molecules make with other water molecules. One of the key features that results in the property of cohesion is surface tension. And surface tension is just a measure of the strength of the water at the surface. Surface tension essentially creates a film on the top of the water, and it does a lot of different things. One of the things that allows it to do is have small bugs are able to walk across the surface of the water. So you can see here some images of various different insects taking advantage of the surface tension of the water. The next property of water that we're going to discuss is adhesion. Adhesion is the attraction between two different substances. So remember, cohesion is two of the same things attracted to each other. Adhesion is two different things attracted to each other. So it turns out that water not only makes hydrogen bonds with itself, water is also capable of making hydrogen bonds with other surfaces. In fact, anything that has a polar surface, water can make a hydrogen bond to, as long as there's a hydrogen there. So glass, soil, plant tissues, cotton, all of these things are things that water is able to hydrogen bond with. This creates a process called capillary action, where water molecules essentially walk up each other whenever they're traveling through a thin tube. A good example of the process of adhesion and capillary action is something called transpiration, and that's the process where plants take water from their roots up to the top of the paper. Up to the top of the leaf. So here is an image of capillary action. If you take a small tube and you put it in the water itself actually begins to walk up the sides of the tube, and it's doing so because of adhesive properties between the water and the tube itself. Here are a couple of images showing adhesion as well. Another property of water that we're going to quickly mention is the water's high specific heat. Specific heat is defined as the amount of heat needed to raise or lower 1 gram of a substance, 1 degree Celsius. This means that water can absorb, well, this property allows water to absorb large amounts of heat with small increases in temperature. So that means that water is able to resist temperature change both in heating and in cooling. Water has a really high specific heat, which again allows it to absorb or release large amounts of heat energy with little change in the temperature of the water itself. This becomes important when we think of something like the ocean. So oceans during the daytime are exposed to a lot of sunlight, and if water was not able to absorb a lot of that energy without big spikes in temperature, the temperature of the oceans would drastically change in day and night. But because water has such a high specific heat, it can absorb a lot of that heat energy during the day, and then give it off at night, which means the ocean waters do not experience large spikes in temperature. And if they were to experience large spikes in temperature, that could be very detrimental to the organisms that live in the water. Here's a look at some specific heat capacities of other substances. So you can see something like aluminum has a really low specific heat capacity. That means aluminum is not going to be able to absorb a lot of heat energy without changes in temperature. Other metals, copper has an even lower specific heat. We can compare all of that down to water. Water's specific heat is really high. It has a value of 1. Another property of water is water's high heat of vaporization. This is largely tied to the one that we just talked about with specific heat. The heat of vaporization is how much energy is needed to convert 1 gram of a substance from liquid to gas. If we're talking about water, in order for water to evaporate, or in order for water to be converted from liquid form to gas form, those hydrogen bonds that we discussed earlier need to be broken. So that takes a lot of energy. It takes a lot of energy to break those hydrogen bonds. One of the things that happens with heat of vaporization is that as water evaporates, as those bonds are broken, it actually removes heat with it. So there's a couple other builds here, but what I really wanted to get at is the fact that water, when it evaporates, takes heat with it, creates a cooling effect. So this is why when we sweat, we are cooling down. Our body is taking advantage of the fact that water on the surface of our skin will evaporate from liquid form to gas form, and when it does so, it'll take some of the body heat with it. That's that cooling effect. Another thing about water vapor to mention now, on the last chapter we talked about greenhouse gases. Well, water vapor is also a greenhouse gas. It helps to form that blanket around the earth, which is important because it can keep the earth warm. The final property of water that we'll discuss briefly is the fact that water is less dense as a solid than it is as a liquid. We know this because if we put ice in a glass of water, the ice is going to float. It turns out that liquid water's hydrogen bonds are constantly being broken and reformed. This causes the water molecules in liquid form to have to be closer together, again because those bonds are being broken and reformed all over the place. But water in solid form, water when it's frozen, actually forms a crystal-like lattice. So the molecules are set at fixed distances. So they're actually somewhat farther apart. We can look at these two images here. One of these images shows water as a solid, and one of these shows water as a liquid. So which one is ice in solid form and which one is water in liquid form? Hopefully we've recognized that in water, in liquid form, the water molecules are going to be close together, and in solid form, or when water is as ice, the molecules are going to be spread far apart and be in a fixed pattern. So all of this is kind of getting at why water is important sort of in our world. It turns out that 75% of the Earth's surface is covered in water. And interestingly, of that, 98% of it is seawater. Only 2% of the water on Earth is fresh water. And of that, A significant amount of it is actually frozen in glaciers and ice caps. The rest of it is in our groundwater, or is in the form of groundwater, which we'll mention later. So from that 2% that's freshwater, only about 1% of that is actually surface and other freshwaters, so things that make up lakes and swamps and marshes, etc. One really important thing when it comes to water is something called the water cycle. The water cycle is a process where you have precipitation, evaporation, and condensation that's occurring, and this actually works to remove some natural contaminants in the water. So natural contaminants in water include things like gases, so radon, nonmetal oxides. It includes dissolved minerals, so that's cations and anions like calcium and magnesium, the things that cause hard water, and also organic matter, which is bacteria and microorganisms, also animal waste. All of these things contaminate the water, and the process of the water cycle actually helps to remove those contaminants. That's important because waterborne diseases are a huge problem. It's estimated that about 80% of all the illness in the water is caused by water contamination. The EPA estimates that 30 million people in the United States are threatened by some type of bacterial contamination in water supplies. A lot of times we think that this is only an issue for developing countries, but it turns out the safety and cleanliness of our water is a problem all over the place. So this is a story, this was in the year 2000, this was published, and it basically what happened was in Canada, and there was a huge outbreak of bacterial infection from contaminated water, and people actually were killed from it. So there was heavy rains and flooding, which caused cow manure to wash into the water supply. And the local utility was aware of that contamination, but they actually didn't report it. And about a week later, a week after the local utility identified the fact that cow manure had washed into the water supply, there were 5 people that had died and over 500 people were sick. And so it's important just to realize water safety, water quality is very important. And if people had been notified earlier, a lot of that sickness could have been avoided. Acid rain is another concept that's important when we're talking about water. We've talked about acid rain a lot. Remember that acid rain is when we have those sulfur and nitrogen oxides that get into the atmosphere, react with water, and produce acidic substances. That acidic precipitation damages the environment by lowering the pH of soil, lakes, and streams. It can also corrode metals and dissolve limestone and marble. Another issue that comes up with water are lakes and dying lakes. So a lot of times what happens is when you have these industrial processes that are occurring, they're going to release their water into the waterways. We also get sewage that gets into our waterways as well. When this happens, the biochemical oxygen demand, or BOD, increases in the water. And basically what that means is that the sewage and other contamination brings bacteria into the lakes, and those bacteria use up the oxygen in the water. So they are increasing the biochemical oxygen demand because now we have these new little organisms that are taking up some of the oxygen. This leads to a process called eutrophication. Eutrophication is a natural process that can be accelerated by the presence of waste. If you've ever gone to a lake and you've seen like gross green stuff floating on the top and it kind of smells pretty bad, that typically is a eutrophication sign. There's a lot of different processes that can cause sewage and contamination to get into our lakes. So when we have just regular rain, that causes something called runoff, and runoff is basically if we have a higher elevation place, the waste from that higher elevation is drained down through various different sources into our water supply. You also have industrial emissions that discharge into streams, and you can have runoff from agricultural activities as well. There's this was a couple of years ago now, but red tide was in the news a lot, And red tide is an algae bloom, and an algae bloom in general, red tide maybe less so, but in general is just a bunch of bacterial organisms that are thriving in the water because of all of the sewage and other waste that's in it. So this is a picture of dead fish that are along the mangroves of Anna Maria Island, which is around Bradenton Beach. If you remember, when red tide came through this area, it killed a whole bunch of marine life and was a big stinky problem. There are other types of algae blooms as well that occur all the time. Anytime you have an influx of nutrients into the water, things that come from sewage like phosphorus and nitrogen, the algae populations explode in these blooms. The algae blooms then take up a lot of the oxygen, which causes the regular aquatic life in the water to die. They also sometimes have fatal toxins in the algae that are released. And scientists think that not only increased runoff in the water, but also increased water temperatures themselves make them more susceptible to these algae blooms. Industrial water use is also a big thing. Manufacturing processes use a whole lot of water, and they then dispose of it as wastewater. So for example, the production of steel in the United States requires 100 tons of water. We also use industrial water for other things, as like, for example, a coolant for electrical power plants. All of that water from the industrial uses is typically pumped back into the water supply because the water itself isn't dirty, they're just using it for other purposes. The problem becomes that can increase groundwater contamination. So there's a lot of different sources of groundwater pollution and contamination, things like storage tanks and pipes that are leaking, seepage from septic systems, irrigation seepage. So there's a lot of things that can basically get contaminated water into our water supply, and it becomes a really big problem when that contaminated water gets into our groundwater. So for example, we can see here the septic tank is leaking and that water is getting into our groundwater, and the problem is when the water gets into the groundwater, there's very little, when the contaminated water gets into our groundwater supply, it can travel all over the place, and there's very little that we can do to actually clean up that contamination from the groundwater. Here's another image that's just showing other sources of contamination getting into the ground supply. Here is just an example of groundwater contamination. So groundwater is easy to contaminate and very difficult and expensive to clean up. One example of something that can contaminate groundwater are nitrates. Nitrate contamination of groundwater is a problem particularly in rural areas. Agricultural activity will contribute fertilizer and animal waste to those water sources. And nitrates themselves are very soluble, which means they can get in the water and they can stay there. So they're very difficult to remove. There's not a lot you can do to remove the nitrates from the water. Infants around 1 year old and younger can metabolize nitrate ions. The problem is they produce something that will bind to essentially to the hemoglobin in your blood and causing you to turn blue. This condition is known as, oh gosh, I'm going to mess it up, so I'm not even going to say it. It's a condition that is commonly called blue baby syndrome. It actually causes death in infants. But in adults, that ion that's produced, it's called nitrite, is actually not as lethal as it is in infants, and it can cause the skin to look blue. It can make you somewhat sick. So the example here, and this was probably, 10 years ago, where they found this group of people and they were all blue, and they had to investigate, like, why are these people all blue? And it turned out that they had nitrate contamination in their groundwater, and all they had to do was stop drinking that contaminated groundwater, and eventually that blue would filter out of their body. But this gentleman here, at least at the time, chose not to stop the consumption of that contaminated groundwater because he was getting a lot of attention in the media for being blue. Another thing that can contaminate groundwater is volatile organic compounds, or VOCs. These add what would I say an undesirable odor to drinking water. Some of them are also carcinogenic. They come from industrial activities, landfills, underground storage tanks, and illegally dumped waste. These are another compound that can get in the water and cause a lot of problems. So what do we do? How do we make water fit to drink? There are more than 170,000 public water systems in the United States. We use almost 2 million liters of water per year. That includes industrial, agricultural, and also personal purposes. The U.S. passed the Safe Drinking Act in 1974, which authorized the EPA to set, monitor, and enforce conditions for water itself. So this image here, what you're looking at is what are the acceptable amounts of various different contaminants that can be in the water. We clean the water at water treatment plants. We do this before it's distributed to homes for consumption. The first step in water treatment is to add something called slacked lime to the water. This will essentially form a solid in the water that takes out some of the bigger things in the bacteria. That all is then removed through filtering and through sand and also gravel. Sometimes charcoal is present to remove odors. Water is then aerated to help improve the taste. Then chlorine is added to help kill any remaining bacteria. Municipal water often contains residual chlorine so that we are sure there is no bacteria in the water. Sometimes ozone is also used for bacterial disinfection. It can also help kill viruses in the water. And finally, ultraviolet light can be used to disinfect the water as well. So again, you add some stuff into the water to settle out all of the gross thick stuff. Then you pass it through some filters, you aerate it, you add some chlorine, and then it is okay to drink. Another thing that's added into wastewater is fluoride. So many municipal water supplies add fluoride to the water to help prevent tooth decay. So this started occurring probably in the late 1970s, early 1980s, the addition of fluoride into the drinking water, and it reduced the presence of cavities or the prevalence of cavities significantly. Some problems is too much fluoride can actually discolor the teeth. And it's not without controversy. There's a lot of people that object to the fluorination of drinking water. This is a slide looking at wastewater treatment. It's in general pretty similar to the water treatment that I showed before. Before wastewater can be returned to the environment, it has to have the contaminants removed. Primary sewage treatment involves holding the sewage in settling ponds to allow the heavier solids to precipitate out so they fall to the bottom at something called sludge. Then we move to secondary sewage treatment where you pass what's left through different filters. During this process, bacteria will break down some of the organic matter that remains. Then the final treatment is to pass it through charcoal filtration to get rid of the rest of the organic molecules, and then it can be returned. That sludge that we were taught, that I mentioned on the previous slide, can actually be used as fertilizer. There are some communities that will take that primary water direct into the marshes, and the marshes themselves can filter and use the nutrients that remain. And there's also composting toilets that avoid all of these steps and just compost the waste naturally without the use of energy or water. And that finishes up chapter 14 on water.